Hello engineers. Hello engineers. Welcome to Vision, my YouTube channel. In this video lecture, we are gonna deal with a topic from structural analysis. And the name of the topic is slope deflection method of analysis. And in the second part of the video, we will be dealing with a question. So let's begin. Slope deflection method of analysis is generally adopted to analyze indeterminate structures. Now, what are indeterminate structures? The structures that require additional equations to the equilibrium equations to analyze the unknowns. Now we can divide the indeterminate structures into two parts as well. The one is ds and the second one is dk. ds is degree of static indeterminacy and the dk is degree of kinematic indeterminacy. While considering the slope deflection method of analysis, we generally take when dk is less than d of s, that is degree of kinematic indeterminacy is less than degree of static indeterminacy. So if we talk about degree of kinematic indeterminacy, we generally talk about the joint displacements available in the form of joint rotation and joint translation, and this is also known as degree of freedom. So let's talk about further into the analysis. This method is also known as displacement method, as we have already written here. Unknown are the joint displacements in the form of theta and delta. The theta is the slope and deflection is the delta. So it comes from the name only. This method is based upon the stiffness approach. And there are a couple of assumptions to analyze the method. And the first one is all the joints are considered to be rigid. That is, all the angle made by the members at the joint do not change. And the displacement is due to the bending moments only. That is, deformations are due to bending moments only, and there is no consideration of axial deformations and shear force deformations. Then moving forward, we have a sign convention here, and the clockwise moments are taken as positive and the anti-clockwise moments are taken as negative. And this goes for the deflections as well. So let's move forward for the derivation part. Now the slope deflection equation are derived by superimposing the end moments developed due to applied load, rotation of joint, and the settlement of a joint. We have taken a section from the continuous beam and we have drawn into a figure. So there are three components: the load, there is this load P, theta A, theta B, and settlement. So while now coming on to the derivation, the first one is due to load P. Due to load P, the load P is acting at somewhere in the beam. We can clearly see that this part is A, and this is B. So fixed end moment developed will be, if the load P is acting at the center, that is A by 2, that would be minus PL by 8, or in this case it would be minus of PAB square upon L square. And this one would be, if the load is acting at center, that would be plus of PL by 8, and if it is acting somewhere other than at center, that would be plus of PBA square by L square. Now the sign convention is, because this moment is acting anti-clockwise, therefore the end moments, fixed end moments developed are negative ones. Now coming forward, it's due to the rotation of joint A. Now if joint A is removed from the fixity and theta A is the rotation given to the joint A, the moment required to produce that theta would be minus 4EI theta A upon L. That would be plus actually because of the clockwise rotation. And the fixed end moment developed due to carryover from the A would be plus 2EI theta A upon L. Now, due to the rotation of joint B, rotation is given at joint B and fixity is removed as well. If moment required is 4EI theta B upon L, then there will be carry over moment to A, and that would be plus 2EI theta B of upon L. And the fourth one is due to settlement of support B with respect to A. Now, if there is settlement of point B with respect to A, we can clearly see that this would act in the anti-clockwise direction. So the value would be 6EI delta upon L square. Similarly, this is acting to make the slope theta 0, that is fixed end moment. So here it will be minus EI delta upon L square. Now superimposing all the values we have got above, we write it down here. End moment for AB would be fixed end moment of AB plus 4EI theta A upon L plus 2EI theta B upon L minus 6EI delta upon L square. Rearranging, we get MAB bar plus 2EI by L 2 theta A plus theta B minus 3 del upon L. Moving forward, we have M of BA bar plus 4EI theta B upon L plus 2EI theta A upon L minus 6EI delta upon L square. Arranging, we get MBA bar plus 2EI by L 2 theta B plus theta A minus 3 del upon L. So these are the equations that we have got for member AB. So I think this is enough for the analysis for slope deflection method for simple members. And let's take up a question for the second part. We will be just taking a shortcut way just to make this video not too big or too monotonous. So if this load is acting 60 kilonewton at the center, fixed end moment will be MAV bar would be minus PL by 8. Okay, that would come out to be minus 60 into 6 upon 8, 3, 4. That will be minus 45 kilonewton meter. The second would be MBA bar. That would be PL by 8. That comes out to be plus 45 kilonewton meter. Secondly, MBC bar, that would be minus WL square upon 12. That would be minus 12 into 6 into 6 by 12. That gives minus 36 kilonewton meter. And the CB section we have plus 36 kilonewton meter. Now moving forward, this is the step for the analysis. We calculated the fixed end moments. Now we do the slope deflections equations. Slope deflection equations. slope deflection equations. Now for MAB, that would be MAB bar plus 2EI by L plus 2 theta A plus theta B minus 3 del upon L. We got MAB bar as minus 45, I think, plus 2 into EI is given. EI is EI. L was 6. 2 into theta A. Theta A would be 0 because it's a fixed time. Theta B is here. And delta would be 0 as well because there is no settlement of support. From here we get minus 45 plus 1 by 3 EI theta B. I think it's okay up to now. Similarly, if we calculate MBA bar, that would be MBA bar plus 2 EI upon L plus 2 theta B plus theta A minus 3 del upon L. That would fetch us a value of plus 45 plus 2 EI upon L. L would be 6 again. Theta is A is 0, delta is 0. So from here we get 2 theta B. That gives 45 plus 4, that is 2 by 3 EI theta B. This is the second equation. Similarly, for the MBC and moments for BC, that would be MBC plus 2 EI upon L 2 theta B plus theta C minus 3 del upon L. Clearly delta is 0, theta C is 0. So we have got, I think, 36. 2 AI upon L would be 6 only. And 2 theta B, that is minus 36 plus 2 by 3 EI theta B. From here we get, and the other one would be MCB. That would be MCB bar plus 2 EI by L 2 theta C plus theta B minus 3 del by L. That turns out to be plus 36 plus 2 EI by L. Now that theta C is 0 and delta is 0, theta B can be taken. Theta B is here. So 36 plus 2 EI by 6 into theta B. These are the 4 equations that we have got from the slope deflection equation. Now the third step is to make joint equilibrium equation or say conditions. That would be conditions. Let's break the members from the joints. This is AB, this is B, and this is B to C. Now if we provide, we can see in the member AB, let's adopt clockwise moment, that is M of AB, that is M of BA. So that this would be opposite, this would be same. This is MBA, M of BC. Now that this is, so this would be, and here, no, actually direction would change because this is the direction here, this is the direction, and it would move more like this. So we have one joint equilibrium equation, that is if anticlockwise is taken negative, MBA minus MB of C would be turn out to be 0. Okay, so putting all the values for MBA and BC here, MBA and BC, we get 45 plus 2 by 3 EI theta B, that this is the equation MBA, and MBC would be plus minus 36 plus 2 by 3 EI theta B is equal to 0. Now EI theta B is twice, so that would be 4 EI theta B upon 3, and the summation of this would be 45 minus 36, that's plus 9, it would be minus 9 if it's go this way. 4 by 3 we have now EI theta B would be minus 9 into 3 by 4, so that would come out to be roughly 36 by 4, that would be minus 7.65 upon EI. This is the value of theta of B. Now putting the value of theta of B into the above equations, we'll get the fixed end moments. End moments we'll get. So writing down the values that I've calculated, MA of B would be minus 47.25 kilonewton meter. MBA would be plus 40.5 kilonewton meter. MB of C would be opposite, plus 40.5 kilonewton meter, and M of CB, that would be plus 33.75 kilonewton meter. That we have got all the 4 values here. Now the next part would be to calculate the reactions. I'll leave you up to here only. To get the reactions, we just put the reactions here, and then we have, remember, A, B, and the other one would be B and C. The reactions are, so let's say this is RA, this is RB1, because RB can be divided into 2 parts. RB2 would be this, and this is the reaction RC. Now this was the rotation. Let's see the rotation for, remember, BC, that was this way. This is clockwise, this is supposed to be clockwise as well. Okay, okay, this is clockwise, both are clockwise. Now putting summation M of at is the equilibrium equation, we'll get value of RA in the same from span AB. Now moment at P is equal to 0. Say if we are taking from span BC, that would give you the value of RC. That would precisely give you the value of RC. Okay, so you have got the RA and RB values, and if you take summation of Fy, that is RA plus RB plus RC, that is equal to the total loads, that was 60 plus 12 into 6, 72 plus 60, 132 I think. So kilonewton is the load. From here we can get RB as well. So we have calculated all the reactions RA, RB, RC. These all three are the reactions, and for the reaction we'll draw a bending moment diagram, and that would finally form a bending moment diagram for this question. So I think it's clear up to now for all of you, and in case some of you are having difficulties, I would request you to go through the lecture again. That's all for today. Thank you.